there, Mrs. Saunders here. Welcome back to the epic Saga of Calculus, where we've witnessed mathematical battles, notational wars, and enough academic drama to win an Academy Award. When we left our story, the dust had finally settled from the great notation wars. Leibniz's elegant dy/dx had conquered the mathematical world. British mathematicians had swallowed their pride, and calculus finally had a universal language. But here's the thing about having a powerful new tool. Once you've got it, you need to figure out what to do with it, what to build with it. Oh, and build they did. The 18th century became calculus's coming-of-age party, where mathematicians discovered that their abstract mathematical toy could solve real-world problems that had stumped humanity for millennia. This is the story of how calculus went from academic curiosity to a practical powerhouse, and how a family of Swiss mathematicians turned problem solving into both an art form and a blood sport. Let's start with the Bernoulli family. This Swiss clan didn't just study mathematics, they practically owned it for 3 generations. At family dinners, instead of arguing about politics, they competed over who could solve the most elegant optimization problem. Johann Bernoulli, who we met in episode 3, emerged as a leading figure in developing practical calculus techniques. But Johann wasn't content to just spread calculus. He wanted to show the world what it could actually do. And in 1696, he issued what might be history's first viral math challenge, the Brachistochrone problem. Picture this. You have a bead sliding down a wire under the force of gravity. What shape should that wire be so that the bead reaches the bottom in the shortest possible time? We aren't looking for the shortest distance. That would be a straight line. We want the shortest time, accounting for the fact that the bead speeds up as it falls. Johann essentially threw down a mathematical gauntlet to all of Europe. Solve this if you can. He gave mathematicians 6 months. The response was immediate and fierce. This wasn't just a math problem. This was a test of who truly understood the new calculus. The solutions poured in from the greatest minds of the age. Leibniz solved it, L'Hopital solved it, and famously, Isaac Newton, despite being in his 50s and supposedly retired from mathematics, solved it overnight and submitted it anonymously. When Johann saw the solution, he reportedly said that he could recognize the lion by its claw. Even in anonymity, Newton's mathematical style was unmistakable. But here's the beautiful part. The answer wasn't just some simple geometric shape. It was a cycloid, the curve traced by a point on the rim of a rolling circle. Mother Nature, as it turned out, already knew calculus. What made the Brachistochrone problem so revolutionary wasn't just its difficulty, it was what it represented. For the first time, mathematicians were using calculus to find the absolute best solution to a practical problem. Not just a good solution or an approximate solution, but the mathematically perfect solution. And this opened the floodgates. Suddenly, calculus wasn't just about an abstract curve or theoretical slopes. It was about optimization, finding the maximum profit, the minimum cost, the strongest beam, or the most efficient design. Johann Bernoulli's son, Daniel, pushed this even further into the realm of physics and fluid dynamics. He discovered that the same mathematical principles governing the Brachistochrone could explain how water flows through pipes, or how air moves over wings, how gases behave under pressure. Calculus was becoming the universal language of the physical world. But perhaps the most impressive applications came from related rates problems, situations where multiple quantities are changing simultaneously, and you need to figure out how fast one is changing based on how fast another is changing. These problems might sound abstract, but they were solving real-world crises. Consider navigation. A ship at sea needs to know its position, but in the 18th century there was no GPS, no radio signals, just the stars and mathematical calculation. Sailors used calculus to determine their location based on the changing angles of celestial bodies. Take the North Star, for example. In the northern hemisphere, its angle above the horizon directly corresponds to your latitude. So if a sailor measures the angle to Polaris at 35 degrees, then they're at 35 degrees north. But now imagine, the ship is moving, and as the angle decreases, the ship is traveling south. By observing how fast the angle is changing and knowing how that change corresponds to their position on the globe, navigators could use related rates to estimate their speed. Lives literally depended on getting these related rates calculations correct. Or consider astronomy. When you're predicting an eclipse or tracking a comet, you're dealing with multiple moving objects, planets, moons, and the Earth itself, all changing position at a different rate. Calculus allowed astronomers to untangle these complex relationships and make predictions that were accurate to within minutes. All of this practical problem solving reached its pinnacle with Leonhard Euler, a mathematician so productive that we're still publishing his collected works nearly 300 years after his birth. Euler found a brilliant young protege in Joseph Louis Lagrange. Through his letters from Germany to Italy and back, Euler mentored this mathematical prodigy. And when a 19-year-old Lagrange sent his breakthrough insights on optimization, Euler was so impressed that he actually held back his own research to let Lagrange publish first. Together, through their correspondence, they created the calculus of variations, methods for finding not just the best value, but the best entire function or shape. You want the perfect curve of a hanging chain? They've got it. The strongest column design? Yep, they can do that too. But what about for future generations? The most efficient spacecraft route. Their techniques gave mathematically perfect answers, but Euler's real genius was seeing connections. The same principles governing the Brachistochrone also explained how light travels through water, how businesses optimize profits, and even how animal populations change over time. Mathematics wasn't just about solving individual problems. It was revealing the universal laws behind everything. Here's where the story gets really interesting. For the first time in history, mathematical discoveries were directly translating into economic value. The merchants who could optimize their shipping routes made more profit. The navigators who understood calculus brought their ships home safely and got promoted. This created a feedback loop that accelerated mathematical development. Practical problems drove theoretical advances, which enabled solutions to even more complex practical problems, and so on. Universities started hiring mathematicians not just to teach, but to consult on real-world challenges. The Bernoulli family, in particular, became mathematical consultants to European royalty. They advised on everything from hydraulic engineering to military ballistics. The young Daniel Bernoulli essentially invented mathematical economics by applying calculus to problems of risk, utility, and decision making under certainty. This wasn't just about individual success, it was about mathematics proving its worth to society. Calculus was no longer just an intellectual curiosity, it was a practical necessity for anyone who wanted to excel in engineering, physics, economics, or navigation. Yet, even as calculus proved its worth in navigation, physics, and engineering, another question lingered. Could these same tools unlock the hidden shapes of the curves themselves? In our next episode, we'll meet the aristocrat who published the first calculus textbook, complete with a rule that still bears his name, and uncover yet another scandal that rocked the mathematical world. From peaks and valleys to concavity and inflection, Episode 5 reveals how mathematicians became explorers of the landscape of functions. Thanks for being here, and I'll see you next time.